Thank you for the invitation to present something in the reading group. And today I will talk about to share some of my reading on network calculus. So first, what is network calculus and why we might be interested in this theoretical framework? Network calculus is fundamentally about providing performance guarantees in communication networks. And it does so through traffic characterization and also a set of analytical tools, including mean plus convolution. And through the traffic characterization and mean plus convolution, it can give proven bounds on delay, both in deterministic manners and stochastic manners. And this performance guarantees is extremely relevant in scenarios where there are strict performance real-time constraints, such as in video streaming, and perhaps more recently in industrial control networks and vehicular networks. So I will also talk about how network calculus characterizes the input-output of queuing systems in a systematic way. And here are some key references. It's the first seminal work was by René Cruz in the early 1990s. And there are two classic books, one by Chen Chang and another by Jean Le Boudec and Patrick Tihan. This presentation draws mainly from these two books, and more particularly from the book by Jean Le Boudec and Patrick Tihan. And I mentioned that there are two ways of guarantees, deterministic ones and stochastic ones. So in recent years, there's more of a development to the stochastic network calculus, which comes after the deterministic network calculus. And also, if you're interested, you could find relevant industrial standards. These are ongoing efforts, including the IEEE sensitive networking work group, and also the IETF deterministic networking work group. And in this talk, we will focus on deterministic bounds. Perhaps some of you are already familiar with the network calculus framework, in which case, feel free to comment. If you're not familiar, feel free to raise questions at any time. Okay, let's take a look at a single queue where there is traffic arrival characterized by a function a of t, and it comes to the queue and there is a server, and the departure is described by a function d of t. And we'll assume that the system is empty at t equals to 0. And naturally, the traffic arrival are non-active and non-decreasing. So is the departure traffic. So there are generally two framework. One is based on continuous time framework, and another is discrete time framework. You could relate one another by through some intermediate steps. Here we will focus on continuous time model for mathematical simplicity. Okay, so here is a figure of the accumulative data in the queue, where you have this arrival traffic described by a of t, and the departure traffic described by d of t. And how do we express the performance metrics that we're interested in, namely the queuing delay and the backlog traffic? From the figure, it is simply the horizontal gap and the vertical gap. Firstly, let's take a look at the horizontal gap, where if you look at the horizontal gap between the arrival traffic and the departure traffic. This gives you the virtual delay, which means that if this queue is first come, first served, then the bit arrived at this particular time instance will leave the queue at this after d of t1. This is the horizontal gap it takes to empty the queue for the bits arrived before t. And yes.
Just a question. So I suppose that one of the hypotheses is that the buffer is infinite.
Yes.
Okay.
If
there is no loss, in fact.
Yes, this is a lossless. Yeah. And for the vertical gap, if we fix a time t, the difference between the amount of traffic arrival and the amount of traffic departure is the amount of traffic that is backlogged in the system. So B of t is simply the difference between these two functions. In this presentation, we will mainly focus on delay bounds, but in a similar manner, one can derive bounds on the backlog. So what do we mean by a deterministic bounds on delay? It means that if we look at all the horizontal gaps, there exists some constant delta, such that if you look at the virtual delay at any time, it is bounded above by this constant delta. So the novelty of the network calculus framework starts with the way it characterizes the traffic. And by this, the first key ingredient is the arrival curve. We say that an arrival flow A is upper constrained by an arrival curve alpha, which is not decreasing, if the difference of the traffic arrivals between any time interval S and T is upper bounded by this function alpha in the time interval. Okay, the first and perhaps the most simple example is a linear arrival curve, which is usually known as the sigma rho regulation. If this arrival curve alpha t is equal to sigma plus rho of t, what it means in terms of the constraints on accumulative data arrival. We could take a look at this figure here. The black curve is again the arrival curve A of t. And this small figure here is the arrival curve alpha of t, which is a linear function. And A of t is upper constrained by alpha of t if we take a look at any time instance and we sum up the arrival traffic at this time instance with the amount of traffic that is constrained by this function sigma plus rho of t, then this function will constrain the arrival curve, the arrival flow. So if you take any instance and do this shifting, this summation and shifting, it will be above this black curve in this figure. Is this clear, everyone?
It's one question.
Yes.
I guess that as in normal life, every link has a finite bandwidth. You
Yes.
take alpha equal to the bandwidth, and you have a regulation function that works.
Yes.
And your goal will be, I guess, to find more tight function to better characterize the arrivals.
Yes.
Yes. Okay.
That's a very good comment because a very an important direction of work is to characterize the arrival curve, and the Actually, there is formally defined minimum arrival curve through this mean plus algebra. But we will not cover that today, but it is a very important and interesting direction. And it also points to, what we will discuss later, which is about the service curve. Because in the case of some finite bandwidth, you have some lower bounded service during any time interval.
Mhm.
So
to answer your question, so it's if you're on a wireless medium, right? So there is nothing like what you alluded to, right? So I mean, anybody can access the network at any time. So then it will not be regulated. So if you take so your view was a wireline situation that arrivals or access when it's not controlled leads to things which are fundamentally non-regulated.
Okay.
And so you had I think your vision was a wireline.
Yes,
With
I'm
the
an
signal.
old guy. Yeah. I don't know.
Fine.
Okay, thank you for that.
yes, that's a very nice comment about the service curve provided by wireline networks and the non-existence of service curve by in wireless network as of now. So how do we guarantee that some traffic arrival is upper constrained by some arrival curve? Well, there is this is done through what is called traffic shaper. You have a input traffic flow, and there is a shaper that shapes the input traffic such that the output of the shaper satisfy the upper constraints of the arrival curve. I will give you the example, which is exactly the previous arrival curve we just saw. This is called sigma leaky bucket. So how does this shaper work? You have a input flow, and it goes into this leaky bucket. How does the leaky bucket work? Okay, you imagine that there is a bucket that has the size of sigma, and this bucket is leaking at a rate of rho at any time. It's a constant leaking rate. So you put the input traffic data into the bucket. If there's room in the bucket, it goes through the bucket at a constant leaking rate, rho. But if the bucket is already full, then the traffic is discarded or delayed. So through this leaky bucket, the output flow will be constrained by the sigma rho arrival curve. And the interpretation of the two parameters, sigma and rho, is sigma is the maximum of burstiness allowed in the system, in the arrival. And the rho describes the constant rate that is allowed in the arrival curve. Is this clear? Okay. And there's an interesting observation, which is simple. If you have a set of arrival curves and that goes into a multiplexer, so the multiplexer takes the sum of the input. If you have upper constraints on each of the individual input curves, then the output of the multiplexer is also upper constrained. And the parameters simply by the sum of the sigmas and the rhos. And so now we come to the second ingredient of the network calculus framework, that is about the service curve. We first look at a typical example, which is the constant rate server. It means that the server will serve the arrivals in the queue with a constant rate C whenever the queue is busy. Obviously, if the queue is empty, then there's nothing to serve. And there is a small exercise to show that the output of this server for any traffic arrival is the inf of the arrival plus the constant rate times the time interval. So perhaps you could take 30 seconds or a minute to convince yourself that this is true.
It's quite clear.
Okay, good. For everyone.
Are you gonna give us the proof?
Yeah, care to share?
the proof.
That's sorry.
I would say roughly that in the worst case, you serve the packet at rate C, which is the second term of the sum. And otherwise, I don't know how to explain it with the worst case. It's obvious because for me, either this is A, which is the dominant term, either this is C time T minus S, and that's why you have to consider to sum them and to take the int.
Yes.
But it's not a clean proof.
Yeah, it's a right. It's the right intuition. We perhaps we could illustrate this by a figure again. If we look at the right side of the figure, you have this arrival curve A of t, and whenever it's not the queue is not empty, the departure is a constant function. So this should be, this is a constant interval. And when the arrival starts to come again and the queue becomes busy, it then starts again with the constant rate. So if you look at any point, the departure traffic, it is the start of the most recent busy period where the arrival traffic equals to the departure traffic, and then you take the sum of this value with the amount of service during the period after the starting of the busy period. So if the queue is always busy, it is simple. It's simply C of t for any t. And if at any time the t is empty, then the departure traffic at that time equals to the arrival traffic. And so the main reasoning of the proof is to look at the start of the busy period. Okay, so now we have the ingredient, which is traffic arrival curve. And then we have demonstrated a service curve, which is the constant rate server. We are now ready to give already the bound on the delay in the virtual delay in the queue. And the theorem goes like this: if the traffic arrival is sigma rho upper constraint, and the server is with a constant service rate that is greater or equal to rho, then the delay, the maximum delay is upper bounded by the ratio of the size of the bucket and the constant serving rate. This part assumes the FIFO first come first serve, because if you are an arriving bit at any time t, it goes into the bucket, you see at most the existing traffic of sigma in the queue, and it takes at most sigma over c time for you to be served. If the scheduler, the server is not FIFO, and if c is greater than rho, then the maximum delay is also upper bounded by a different constant, which is the ratio of sigma and the difference between the service rate and the arrival rate. How do we say this? If you go back to this curve, the maximum delay of any bit starting from any time is upper constrained by the length of the busy period it is in. Okay. So let's assume that the busy period is big T. Okay. Now we have the amount of because it's a busy period, the amount of departure c times t is upper bounded by the amount of arrival in that time interval, which is upper bounded by the nature of arrival curve, sigma plus rho of t. And if you move t to the left-hand side of this, you obtain the upper bound on the length of the busy period t. And this gives you the proof for the maximum delay. So we looked at an example of a constant rate server, but in general, the service curve can be more generally defined by an inequality instead of equality. The definition of service curve is that a system has beta of t as its service curve if the amount of departure at any time t is bounded below by the inf of the summation of these two parts. The first part is the arrival at some time s, and the second part is the service curve function at the time interval. But here, this is not a product, beta TOS, it's a function. So if we compare this with the previous example, d of t equals to this, it's simply a generalization of the constant rate server, and also a change of equality to inequality to become a lower bound. And this is the key result that we immediately obtain after the definition of the service curve and the previous definition of arrival curve. And it goes like this. If an input flow is upper constrained by an arrival curve alpha, and it traverses through a system that gives you a service curve beta, then the maximum virtual delay is upper bounded by d of the distance between alpha and beta. And what is the distance between alpha and beta? It is simply the greatest horizontal gap between the two curves. Okay, so if you look at the inside of this definition, this is the horizontal gap at some time s. And if you take the supremum over s, this gives you the greatest horizontal gap. Okay, so now we are in a position to introduce the mean plus algebra. If you are already familiar with the definition of the mean plus algebra, you would have noticed that it appeared already in our previous definitions of arrival curves and service curve. We introduced the formal definition of mean plus convolution. And if we take a look at this definition and the definition of the service curve, you will observe that equivalently, we say that beta is a service curve if d of t is greater than or equal to the mean plus convolution of the input arrival and the service curve. Okay, and if the same name convolution hasn't ring anything, here is a more clear analogy of the mean plus convolution to the classical system theory. If we take the plus and replace it by a product, and if we take the inf and replace it by an integral, then it is you retrieve the classical definition of convolution. So in a similar manner, this defines the convolution between two curves, similar to the convolution of two signals in system theory. And it actually goes a bit beyond that, which we will see shortly. Some general properties of the mean plus convolution. I will not provide proof here, but you might convince yourself that it's a simple exercise to show that it is associative. So the convolution of two functions and convoluted with another function is equivalent to the first convolution of the last two functions with the first function. And it is also commutative, which means the change of order of the two functions doesn't change the convolution result. And it is distributive with respect to the operation of mean, which means that if you take the minimum of two functions and its convolution with another function, it is equivalent to first taking the convolution of the two functions respectively with h, and then taking the minimum of the two functions. Why are these useful, and what is the further connection of the mean plus convolution to the system theory? This is demonstrated by the concatenation of queues. Okay, we discussed the single queues already, and now we look at a concatenation of a set of queues. Okay, you have an input arrival flow, and it goes into the first queue with some service curve beta 1 of t, and it comes out, and the output is again poured into the second queue, which has a service curve beta 2 of t, and then you could it goes on and on, and you have an output d of t. It can be proved that the concatenation of the servers has a service curve beta of t, which is simply the mean plus convolution of the set of service curves provided by each of the queue. Okay, how do we prove that? It is actually very straightforward. If you take the output d of t, by the definition, the d of t is lower bounded by the convolution of its own input a star of t with this service curve beta 2 of t. And by the definition again of the service curve of the first queue, the departure is lower bounded by the convolution of the arrival flow with its own service curve. So you have the second inequality here. And then by the associative property of the mean plus algebra, we could associate beta 1 and beta 2. And this gives you the mean plus convolution of these two service curve, which gives you the new service curve of the system. Okay. And here is a simple example. If we consider again an input which is sigma rho regulated, and we consider two servers, each with service curve that is a constant delay, and after the constant delay big T, you have a constant serving rate. Okay, the two functions are of the same nature, and two set of parameters. So if we do the calculation, the mean plus convolution of the two service curve is actually very simple, and you could show that it is simply another function of the same formality, but the serving rate is the minimum of the two serving rate, C1 and C2, and with a delay that is the summation of the individual delays by the two service curve. So here is your new service curve after the concatenation of the two queues. And by the delay bound theorem, okay, we have the distance between the arrival curve, which is sigma plus rho of t, and the new service curve, which is a delay of t1 plus t2 and a constant rate, which is the minimum of these two. And you could see, you could easily calculate the maximum horizontal gap between the two curves. And this gives you an upper bound on the virtual delay. Okay, to summarize, we discussed the arrival curve, and we discussed the service curve as well as mean plus algebra. The core principle of the framework is that if you have, if you would like to have some deterministic guarantees of the system performance, then it is then you have to put constraints on the amount of traffic allowed into the system, and also a lower constraint on the amount of service rate that you have provided by the server. Okay, this could be a contract between a service subscriber and a service provider. And we show that the mean plus algebra can be used to characterize the input-output relationship of a system of concatenated queues. So I have, thank you very much.
Who shoots first? Marco?
Yes. So you explained in your last slides that you have a relationship when you have some queues that are concatenated. But in networking, in wired networking, sometimes you have some parallel paths.
Yes.
And so I was wondering if there was something in network calculus that deals with this problematic. I guess there are, it depends on the strategy of the load balancer or something like this, I guess. And so that's my question. Is there something?
To make sure I understand the question, you mean that there are,
You have two links in parallel to reach your destination, for example.
okay,
And so here you explain that you could rely on the convolutions to characterize what happens when you concatenate some queues. But here in what I describe, you have some paths that are parallels.
okay.
And so I was wondering if there was some mathematical formulas dealing with this kind of graphs.
So you have two, let's say, two traffic arrival into the same queue, and then it goes on.
Or even a single arrival that dispatch into two paths.
Ah, okay. Yes.
And then that join once reaching the destination.
Yes, yes. There are results described in the book. Yeah.
Okay.
Other questions? Don't be shy.
It isn't the kind of multiplexing
The multiplexing is when you have multiple
on the same
arrivals.
server.
Yes, but I think he's having
Multiplexing, I guess.
Okay.
a more
Okay.
general scenario with multiple input and also multiple outputs, and
Okay.
there's a involved relationship of the queues.
I think if you have two queues in parallel for a split traffic flow, it feels like it operates as one queue with different arrival and departure functions, but it's still you should be able to aggregate arrival and departure functions to have it appear as one single queue. If I'm not mistaken, depends on the strategy for dispatching. You won't have the same arrival constraints.
That depends heavily on the nature of the scheduler. How, for instance, if there are priorities in the input traffic, and if the scheduler prioritize serving one class of traffic over the other, then you could get completely different performance for the different this split of the curves.
I have another question.
Sorry, you want
Just a
to-
point, in Chang's book, at the end of chapter 2, you have a fantastic link, which is the Jackson network. You know the Jackson, yes.
By name.
Yes, you have feedbacks, you have routing, and if you indeed add constraints on the routing mechanisms, you can handle feedback. You can also add all the bells and whistles and get end-to-end delay for traversing the network, even with feedback and routing. So he has managed to do that for Jackson. And it varies quite well with mean plus operations. So the mean would, like in the Leaky bucket, we wait for the latest of the ends packet here and ends packet there. And so, and the delay, so there is a wide class of systems. I mean, this is a very essential question, but yes, it's amazing. At the end of chapter 2, you have this example.
Okay.
And it's highly non-trivial. The fixed point.
Yes, I guess.
For feedback.
Which book is?
Chang's book.
This is for arrival rates that are deterministic functions. Not,
No.
That's the problem.
Arrival rates are just you have service curves everywhere, plus reasonable assumptions on the routing. And feedbacks, everything, right? And then you can prove end-to-end delay for traversing.
Maybe I will give Marceau the opportunity to ask a question, and then maybe you again, Marco. Go ahead, Marceau.
Yes, I just want to know if you are aware of extensions to wireless networks.
So perhaps based on this presentation, the part that was not discussed is the stochastic guarantees. The idea is similar to the deterministic guarantee, but the difference is that you, instead of having a deterministic function that constrains the input arrival and the output service, you have assumption on the tail distribution, on the distribution of the arrivals and the departure. And if you have these probabilistic constraints, then you could have a bound on the probability that your delay exceeds some large value. So those would be the stochastic guarantees for such assumptions. And this type of assumptions could be applied to wireless networks.
Okay, thank you.
Is it related to the HO information?
Well, I mean, the age of information is defined based on some different form of the delay. So it's related to delay, but it's not directly the same. But in a similar manner, I guess you could obtain bound on the maximum age of information in a similar manner to having bound on the delay here.
Other questions?
I have
Francesca?
another one. So discussing about wireless networks, when you have your arrival shaper, traffic shaper, in a wireless network, the thing that do not go in the shaper get retransmitted. So can you make an evaluation stochastic bound of the delay, taking also into account the retransmission, or it's not done? Maybe it's not done. Maybe it's out of the scope of.
That's a great question. I would assume that maybe someone has looked into this problem, given the amount of interest in extending performance guarantees from wireline to wireless, and also the retransmission is a fundamental mechanism.
Yeah.
So I would guess that this problem has been looked at. Perhaps not to the extent of depth.
Maybe in the context of age of information. From I mean that was the thought that I had.
Yeah, if retransmission is modeled, it's
You need to model retransmission. Yes. Thank you.
But I think it's basically impossible. Because, I mean, if you have, like in the discussion with Marco, right? So, I mean, assume, I mean, if there is no constraint on the arrival, we have an avalanche of arrivals, right?
Yeah.
I mean, like, I don't know, 10 to the 18 packets that come. So, and then, I mean, if you make them wait, you cannot give guarantees to these guys. So we can retry or wait this day. So basically, I mean, if the thing is completely wide, and you don't pacify it, it's still wide.
I agree. But the difference to me is that when you do wired, you can lose things, but then you recover them like very, very high and like closer to the application. When you do wireless, you know you're going to lose stuff, so you know you're going to retransmit all the time. I think it's like 10% of packet loss at the first transmission that you target when you do a mobile network. So retransmissions are very frequent, and so I thought that maybe there was somebody who, well, looked into that. But yes, modeling how you're going to retry something that you lost is
If you are persistent, I mean, and there is an avalanche which is the size of the number of particles in the universe, which is possible Poisson, then you are dead, right? So, and I'm not even
Agreed.
going to come back, but
The problem is deterministic network calculus, but with stochastic network calculus, you can take it on that.
yeah, but then for that, right? Yes, sure, indeed, and that's
You do?
I have a question. So it is related to my very first question on your presentation. Here you have you model your queue. The queue can be infinite. Are there some modeling? Are there some adaptation to this model in which you bound the size of the queue, and if the queue is overloaded, then there are losses. And are there some works using deterministic network calculus using this kind of model with finite queues?
I would assume that there are. If someone is aware, feel free to point out. But also, for some type of traffic, you might have already.
That's a good question.
Yes, you might already have a prediction of the maximum queue size, I mean buffer size that you need for the system.
So maybe you answer my second question I had here. So here we look only on the delay in the presentation, and you told us that there are also some results on the backlog. And knowing the backlog indeed is interesting to know how to dimension the queue to avoid losses. And so my question was, are there some similar results in the community queues about the backlog, about backlog bounds for each queue?
Yes,
Yeah.
I think so.
I suppose yes, but as I am not working on that.
Yes, the reason I think that way is because the definition of the backlog and the delay, they are
Almost similar.
yes.
Answer this with debug. You can imagine this in real network, the bandwidth is quasi unlimited. So you can, if the queue comes, if the density of the arrival is very high, you can increase the bandwidth of the service. So you can increase your service rates in parallel, and to reduce the possibility of backlog. Because
But if you can increase the bandwidth, you know when to increase it. So you need to know the backlog, the current backlog. So this is why I think you need still to have an evaluation of the maximum backlog given some capacity.
I don't know how it works, but I agree that there is an implementation by Google of bottleneck control like BBR algorithm that consider this problem.
So in fact, in many of the references, they are the delay and backlog. They appear in parallel to each other. It's like a bundle. So if you have one, you have similar results on the other.
I suppose you have something similar to with a mean plus algebra adapted to the backlog, I suppose, or you are doing. Maybe what I said is
I think
is
so.
not correct.
Yes, I think so. Yes.